This is lecture 21 for Chem 223. Today we will be talking about ion exchange chromatography and Lab 8. This is the column that will be used for Lab 8. So it's literally just a clear plastic tube with some structure at the beginning and end so that you can load your beads in here. And your beads will come into about this height right here. We're not being super quantitative with how many beads we add. We just basically need a minimum number of beads. We can have more than that if we need. And then I wanted to review some of these LU words. So the first one is elution. So elution is passing an analyte through a column. I know I've used that word before, but I wanted to review it here in case anybody was unclear. Your eluent is what you put into your column. So that is your analyte solution before it goes in or as it's going in, and your eluate is what comes out of the column. And right up here, you'll notice there's two lids actually. So there's this bigger lid you can unscrew, and there's a little top you can pop off. I generally just do everything through the big unscrew top. And at the bottom here, there's a little knob you have to pull off to get the solution to flow out as well. So if you're trying to load the column, you'll put that little knob back in. And these guys are stored in deionized water or with deionized water in them. So when you're done with it, you'll refill it. However, if you don't get through the whole lab in one day, you can actually store this column with the beads in it in your drawer. I suggest simply adding distilled water to the column and the beads and then just placing it in the drawer and like that. So let's get into the theory of what's going on in Lab 8. So what I have here is a picture or a representation of the beads in the lab. They're all brown to tannish. And on the surface, they have a bunch of these sulfate groups with an O- sticking out into solution. So the way this is going to work is first you need to make sure that there is a proton on each of these O- groups so that we'll have something to exchange. So the way we put protons on there is we just wash a strong acid through. Usually we use HCl for that. And that just ensures that there are enough protons present that every one of these O- groups is protonated. Then when you send your analyte through, anything that has a positive charge will displace some number of protons. And what you'll notice is that for each of these 2+ ions, 2 protons were replaced. If this had been a 3+ ion, it would have displaced 3 protons. If it was a 1+ ion, it would have displaced 1 ion, or 1 proton. If it was a negatively charged ion, it would not have interacted with the bead and simply flown through. So now we've gotten all these positive protons popped off of our bead. It's a hard sentence to say. And now we need to figure out how many of these protons we displaced. And by finding out how many protons we displaced, that's how we'll find out how many ions we actually added to our beads in our columns. So what we're going to do is just send water through here, and that's going to wash these protons down into a beaker that's under our column. These ions up here are going to stay on the beads. We aren't able to get those off, or we don't want to get them off necessarily. What we're going to do is titrate that beaker we just diluted all those protons into. So we're going to stick it under a burette and titrate it with NaOH to figure out how many protons were there. And notice that we're not trying to figure out the concentration of the protons in the beaker. That doesn't really matter, and it depends a lot on how much water we use to wash through the column on multiple steps. And so what we're trying to figure out is the number of moles of protons, or in other words, the number of protons we washed out of there. Right, and then when we're done, we're going to try and wash this column off by sending more protons through to displace the ions that are already stuck to the beads. So you're probably wondering then, well, what controls what sticks to the beads? It's binding affinity. So if you have something that sticks to the bead more strongly, especially if it's a 2+ or 3+ ion, that's always going to be more favorable than a proton. Things like sodium and potassium that have the same charge as a proton but have slightly different volume, slightly larger ions, actually have a lower binding affinity to the beads than protons, but you have so many places where the sodium and potassium could potentially bind that it's just a probability game at that point, where the odds are on your favor that you'll attach a sodium and potassium. So then how did we replace these ions with H+? Well, again, this is a probability game. What we do is send through a highly concentrated acid that's full of protons, and those protons, each proton has a small chance of replacing a big ion on the bead. And so if we put in just tons and tons of protons, then we get up into a substantial chance that we'll displace the ions and move them down the column. And in reality, when we do this lab, we usually don't get the ions all the way off the column. The vanadyl sulfate that you put into the column leaves a blue band, and you can usually see that throughout the column, or it gets spread out and turns your whole column green, which is totally fine. And there's generally still plenty of places or plenty of beads to interact with future samples. But to get your ions completely off the column, you just have to keep washing acid through for a long time until the statistics work out in your favor and all of the ions are washed off the column. Now, let's see if you understand this concept. I'm going to give you this question that's a practical application of what I just talked about. So if 10 mils of a solution containing 0.2 molar iron 2 plus and 0.1 molar iron 3 plus is eluted through an ion exchange column saturated in protons, how many moles of protons will elute from the column? All right, so your beads are covered in protons. We're sending this analyte solution through. Go ahead and pause the video now and see if you can answer this question. Okay, here's how you'd work this out. So first we need to figure out how many protons were released per ion. So what we're going to do is figure out how many protons the iron 2 plus released from the column and caused to elute down into our beaker. So what we'll do is we'll take the concentration of the iron 2 plus, which was 0.2 molar. We'll times it by the volume of iron 2 plus solution we put through, which was 0.01 liters or 10 mils. And we'll multiply that by 2. Why are we multiplying this by 2 right here? It's because iron 2 plus has a 2 plus charge. So it's displacing 2 protons for every mole of iron that we send through there, or every atom of iron we send through there. So the iron 2 plus displaces 0.004 moles of protons. And then we can do the same thing with the iron 3 plus. It had a concentration of 0.1 molar. And again, we sent 10 mils through. And we are multiplying by 3 because it has a 3 plus charge state. So we're going to be displacing 3 protons for every atom of iron 3 plus. We send through there, and so we get 0.003 moles of protons out the other end. And so the question then is, how many moles of H plus will elute from the column? And so we need to figure out the total number of protons. And so to do that, of course, we'll just add this 4 and 3 together to get 0.007 moles of protons total released from the column. Now, I like to ask this question before having you answer the next question, because generally, if I don't ask this question right now, people struggle a lot on the next question. But having worked through this problem, generally a lot fewer people struggle on this next problem. All right, here is the problem. If 10 mils of a solution containing an unknown amount of vanadate 2 plus and copper 2 plus is eluted through an ion exchange column, and 0.009 moles of H plus are eluted, what are the concentrations of the VO2 plus and copper 2 plus? So this one we're working a little backwards from what we did last time. Go ahead and pause the video now and see if you can't work through this. All right, here's how we're going to do this. We already know the total number of moles of protons that came off, right? That was given in the question. It was 0.009 moles. So we have to track down how many moles of those came from the vanadyl sulfate or the VO2 plus. I don't have the sulfate, I guess, in this question. And we also have to figure out how many protons came from the copper 2 plus. So we'll set up our equations just like last time. So our number of protons from the vanadate 2 plus is equal to the concentration of the vanadate 2 plus times the volume we used, which was 10 mils, times 2 because this has a 2 plus charge state. And we'll do the same thing for the copper. We'll get to this point, and then we'll run out of steam because we don't have enough information here to solve this problem, right? We need one of these values to be able to solve for the other one. or we need at least some more information about them to solve this problem. So I like to throw this problem here as well, just to help solidify the idea in your mind that we can't just magically pull out numbers from nowhere, okay? Now for this lab, the unknown is a vanadate sulfate solution. And the bottle states that the purity is greater than 90%. And I'm actually giving you what the impurities are in this compound. The impurities, or at least the major impurities that contribute significantly to the weight of this thing, are sulfuric acid and water, okay? And then it's gonna be your job to figure out how much the sulfuric acid and water and vanadate sulfate contribute to the overall composition of this compound around now. And you'll also get a magnesium 2+ sample to analyze separately. Well, let's talk about how you're going to figure out the relative amounts of vanadate sulfate, H2SO4, and water in the unknown. So I'm going to give you an unknown, and I'm going to give you the concentration of that unknown in grams per liter. So that's how many grams of this vanadate sulfate unknown I added to the bottle and then diluted it. And by me, of course, I mean the stockroom people, because I don't like to do real work. I'm a professor. Now, that unknown weight is going to consist of the vanadate sulfate, H2SO4, and water, and the weight is just going to be 8 grams per liter. It might be something like 8.01 or 7.99, but it's generally about 8 grams per liter. And you're going to have to do experiments to figure out how much each of the components contributes to that overall 8 grams. The way you're going to start is by sending a sample of that unknown through an ion exchange resin. You're going to elute out the protons that get released from that column. When you do that, what information is that going to give you? Well, you actually have 2 species in here that provide protons. You have the VO2+, so that's from the vanadate sulfate. The vanadate sulfate dissolves in water to give you the VO2+, or the vanadate ion, and the sulfate ion separately. So as the vanadate ion passes through the column, it's going to displace 2 moles of protons for every mole of the vanadate sulfate. And H2SO4, this is an acid with 2 protons. And so you can think of these protons as either displacing other protons on the column or passing straight through the column themselves. Odds are these protons from the H2SO4 will interact to some extent with the beads on the column and probably displace some other protons. But you'll probably also get a handful of the original protons through the column as well. Either way, if you put H2SO4 into the top of your column, you're going to get 2 protons out the bottom of it. Okay, so when you do this titration of your ion exchange eluate, you're going to figure out the total concentration of the vanadate ion and the H2SO4 together. And then what you're going to have to do is determine the vanadate sulfate concentration separately using spectrophotometry. So then you'll have the concentration of the vanadate sulfate. You'll be able to use that with the information you got from the ion exchange resin to figure out how much H2SO4 is in there. And then you'll be able to use both those values to figure out how much water is contributing to the mass. Let's do a practice calculation here just to make sure you can handle this. Okay, so the stock solution, or the unknown, is 8 grams of solid and 1 liter of water. You're going to do spectrophotometric analysis of the unknown. You're not going to dilute it at all, actually. You're just going to stick it straight into the UV-Vis instrument, and you get an absorbance at 750 nanometers of 0.700. And in this lab, you don't actually have to do a calibration curve to determine the molar absorptivity. I'm just going to give that to you in this lab. You're welcome. The molar absorptivity for the VO2+ at 750 nanometers is 18.01 per mole per centimeters. Okay, so then you have that information, and then you send 10 mils of the unknown through an ion exchange resin, and then wash all the protons that are displaced off into a beaker. And it takes 40 mils of 0.02 molar NaOH to reach the endpoint of that titration, meaning that that's how much NaOH it took to titrate the protons that came off. Now what I need you to do is determine the number of grams of vanadate sulfate, H2SO4, and water within the original 8 grams of solid in the stock solution. Something I almost always forget to give you when I put this problem up is the molecular weights of these guys. Now here I'm giving you these masses in whole numbers, but of course you should use as many decimal places as you can find to do your actual calculations. All right, go ahead and pause the video now and try and work through this problem. All right, now let's go ahead and go through the solution so we can figure out the composition of the solution. Ooh, double meaning, the word solution. So we'll start with our spectrophotometric analysis. Now we have Beer's law here. We got our absorbance from the instrument, so that's our measured value. I gave you epsilon, and you should have used a 1 centimeter cuvette for this. And so what we're trying to solve for is our concentration. So we'll solve Beer's law for concentration, right? We get concentration equals A over epsilon B. And at this point, we can just plug numbers into these values. We have our absorbance of 0.7000. Our molar absorptivity is 18.01 per mole centimeters, and we have 1 centimeter path length. And that will give us a total concentration of 0.0389 molar. Now notice that this is just the concentration of the vanadate ion, but of course that's also the concentration of the vanadate sulfate complex, if you want to think about it that way. So we need to take this concentration now and figure out how many grams of vanadate sulfate we have. So we're just going to take that concentration, times it by the volume of unknown that we made, and that was 1 liter. So I put 8 grams of unknown in 1 liter of water. And of course, multiply by the molecular weight here, and that gives us 6.34 grams. So now we know how much of this unknown is being contributed by the vanadate sulfate. Next, we're going to analyze our titration data. So what we know is that as we passed our unknown through the ion exchange resin, we displaced some amount of protons. Those protons we washed down into a beaker, and then we titrated that beaker with OH minus, or sodium hydroxide. And we know that sodium hydroxide reacts with protons at a 1-to-1 ratio to form water. So we know the number of moles of OH minus are equal to the number of moles of H plus that we put in there, and we can solve for the number of moles of OH minus. That is the volume of OH minus we used, which was 0.040 liters, times the concentration of the OH minus we were using, which was 0.02 molar. That gives us 0.0008 moles. So that's how many moles of protons were washed out of there. And then we can use that information to figure out our total concentration of the vanadate sulfate plus the H2SO4 here, right? So those are going to be equal to the number of moles of protons. And we're going to divide that by 2 because these both contribute to 2 protons to our solution here. So we're going to divide that number by 2. If these ions were different, let's say one was a 2 plus and one was HCl instead of H2SO4, this math would get a little more complicated. We couldn't simply divide by 2. We'd have to account for all the different charges, etc. But we're not going to worry about that just now. So then we're also going to divide by the volume of our vanadyl sulfate solution that we put in there, and that was 10 mils. So we'll take our 0.0008 moles divided by the 10 mils, and of course divided by 2 for the charge to find that the total concentration of the vanadate and H2SO4 together was 0.04 molar. And that's not something you consider a lot, is the combined concentration of 2 species, but why not? Well, because it's usually not useful, but it is useful in this case. All right, so now we know that total concentration, and we know how much of that concentration is provided by the vanadyl sulfate. We just need to find the difference there to find out how many moles or how many grams are being contributed by the H2SO4. So our H2SO4 concentration is going to be equal to the vanadyl sulfate plus H2SO4 concentration minus the VO2 plus concentration, and that'll give us 0.0011 moles. Of course, we can turn that into grams the same way we did for the vanadate sulfate. We take that concentration, multiply it by a volume of 1 liter, because that's how much we started with, multiply by the molecular weight of H2SO4. That'll give us 0.11 grams of H2SO4. Now we know that we started with 8 grams total. We know how many grams were vanadate sulfate, how many were H2SO4. So then we can solve for the number of grams of water simply by subtracting those two values from 8. Okay, let me know, of course, if you have any problems or confusion about that. I'll be glad to help you out. Now for the lab, although the lab procedure doesn't specifically say it, you should use a water blank when you're setting up your spectrophotometric analysis. And I am actually not going to tell you what your blank should look like in this lab. In this lab, I'm going to let you squirm and figure that out for yourself so that you may grow as a scientist. All right, be frugal with the stock NaOH solution. Don't pour 500 mils into a beaker and carry it away. That often happens and it just causes shortages and so forth. So just take what you need when you need it every time. I know that's a little less convenient than just taking a big amount away with you, but we always just run into problems when people take big amounts away. And we often actually run into spills. So I'm going to discourage you from doing that. But on the other side, you don't have to be frugal with the resin beads you add into your column. Now, of course, here it says go nuts. I don't want you to go too nuts, but the amount that is listed in the lab procedures, it should actually be treated as a lower limit on how much resin you should add in there. If you're having trouble getting reproducible results, I generally recommend doubling the amount of resin you have in there. You're not going to lose much by adding more resin. In fact, you almost lose nothing at all in terms of time, but you generally gain much more reproducibility by adding more resin. And the reason for that is if you have more resin, you're more likely to get 100% or nearly 100% of your analyte ions interacting with your beads. So if you have too few beads, you're going to let some of your analyte slip through cracks and holes in there, and that's not what you want. Now for real-world applications of ion exchange chromatography, there's actually a lot. The one that people are most familiar with, or at least interact with the most, is soft water generation. So in soft water generators, you're just exchanging things like calcium and magnesium, and usually a couple other metals for sodium or potassium ions, most commonly sodium. So you're actually not reducing the salt concentration in your water, and it actually, since these are usually 2+ ions and this is a 1+, you're actually increasing the number of ions in your solution. You're just changing it to a more gentle ion, one that's softer on your pipes. It's also used to remove heavy metals like copper and lead from water for water purification systems. This is essentially the same as a soft water generator, but we use it in a different context, and so it gets its own category. And it's also actually often used to remove radioactive waste from waters. So for example, if you're working in a nuclear power plant, you might use ion exchange chromatography to remove any dissolved uranium and plutonium from your water before you stick it into your lake. That way you don't end up with a three-eyed fish, especially a three-eyed fish that glows. And my favorite application that's listed on here, this was one I actually found out from Dr. Jeff Macedoni, is that some companies will actually use ion exchange chromatography to remove bitterness from orange juice and other citric juices, but I think mainly just orange juice. So the reason they do this is a lot of cheap oranges that are easier to grow, have tons of this species. This is limonic acid. And limonic acid is really bitter. You can taste it actually at super low levels. So the human tongue is a great detector for limonic acid. And so if that's in there, your orange juice just doesn't sell and people hate it. And so one solution to that is to grow the really expensive oranges. Those just have very little limonoic acid or sometimes none at all. And then your orange juice will sell. But a cheaper way of doing this is actually just sending your orange juice through an ion exchange column. And you'll see that this limonoic acid has a few acid groups on it, and these can be negatively charged in the proper context, usually just any orange juice, they're negatively charged. So you just send that through an anion exchange column, And that'll pull out this limonoic acid. It'll also pull out a lot of other acids like citric acid and so forth, or at least lower their concentrations. I'm pretty sure Southwest Airlines uses the cheaper type of oranges that are full of limonoic acid, and I'm also pretty sure they make no effort to try and remove the limonoic acid. But I'm guessing their idea is, hey, we've already got them trapped in this can 7 miles up in the sky. What are they going to do? So their orange juice is terrible. I actually have a paper about this attached to this PowerPoint. So if you're interested in that, you can look that up. Right? If you have any questions about ion exchange chromatography, feel free to let me know.